Okay, in this lesson we're going to use the Law of Biot-Savart to determine the magnetic field strength at a point above a long wire. So let's put this wire on an XY axis. And we'll try to figure out what's the magnetic field at that indicated point. So when we use the Law of Biot-Savart, we need to picture the little element ds. So let's picture a few of them. So there's the very first ds we have to account for, and we'll imagine a case where current is flowing to the right. And then there's another ds, and there's another one, and so on. So I don't know, let's just at random choose this one. Okay, and then we need to picture r. So r is the distance between the ds that we've highlighted and the point at which we're trying to find the magnetic field. So the vector r hat is a vector 1 unit long pointing along that line. So we've got the full distance of r, and then we've got r hat, and ds is this vector that points to the right because we say current is flowing to the right. Okay, so we can picture what r hat and I and everything else is just constants. So now let's figure out the direction. So it's ds cross r hat gives us the direction of dB. So ds is a vector pointing to the right. R hat is a vector pointing up and to the right. And so this would be like asking, what's the direction of the vector A cross B? And as you know, A cross B would be a vector that points out of the page, whereas B cross A, if we had that same arrangement, would be a vector that points into the page. But we have A cross B, right? It's not R cross ds, it's ds cross r hat. So indeed, the direction of dB is out of the page. And if we were to choose a different ds, maybe this one, it would still be the same situation. Now, if we compare these two, the difference is this ds has a larger value of r, this ds has a smaller value of r. So for every unique ds, r is going to be a different quantity, and so is this value theta going to change, right? And so is the value of x. But the one thing that's the same for any ds is the value of y, if we select this as the point at which we're trying to find the magnetic field. So let's continue. If I want to get the overall magnetic field at this point, then I need to integrate all the contributions to the magnetic field from each and every one of these ds. Okay, so that means I have to take the integral of mu naught over 4 pi I times the product or the cross product of ds and r hat, all divided by r squared. So as we've shown, every ds has a different value of r, so we can't take that out of the integral. But the same current flows in every one of these little elements ds, right? There's just one single current that flows through the full wire. So in step 3, we'll take out of the integral all the values that are constant, and that gives us mu naught times I over 4 pi times the integral of ds cross r hat over r squared. So ds cross r hat, let's see, r hat is just a vector with a magnitude of 1. So all we're really doing is multiplying ds times 1, but because it's a cross product, we can think of it like this. When I try to take the cross product of ds cross r hat, I could picture it more like this. I can say leave the ds alone and break r hat into components. there's a component of r hat to the right, and there's a component of r hat that points up. And there is no cross product between this component of r hat and the vector ds. It's only this component. And this component of r hat would be r hat sine theta. So ds cross r hat is just the same thing as ds times r hat times the sine of the angle between them. So we have an angle of theta in between ds and r hat, and that's the angle theta shown in this diagram. So step 4, b equals mu naught I over 4 pi integral of, now ds lies exclusively along the x-axis, so there's no distinction between ds or dx. So let's write it like that. Instead of ds, we'll call it dx. We don't have to write the magnitude of r hat because that's just 1, and then we're left with a sine theta all divided by r squared. So there's 3 variables here. We've got x, we've got r, and we've got theta. And just to illustrate one more time, for this long straight wire at a point P right here, if I choose ds number 1 and compare it to ds number 2, ds number 1 has a large value of r, ds number 2 has a smaller value of r. X number 1 is a big value, x number 2 is a small value, theta number 1 is a small angle, and theta number 2 is a larger angle. So all 3 of these vary for each different ds. So I can't take any of those out of the integral. And really what I should do is get everything in terms of one single variable. So how about we look closely at this right triangle right here. Let me draw that again over here. So there's theta. This distance is y. Okay, so that's y. This distance is x, and this distance is r. So let's just take all of our trig functions. Cosine theta would be x over r. Sine theta would be y over r. And tangent theta would be y over x. So I'm going to rely on the fact that the only thing that's constant for the different indicated ds values is the value of y. X, r, and theta all differ, but y is the same. So we can use that to try to get everything in terms of one variable, and the one variable we'll try to put everything in terms of is theta. So let's rearrange this, and we can say r is equal to y over sine theta when we cross multiply. But then again, if we look back at our step number 4, we have an r squared, so we can say r squared equals y squared over sine squared theta. But then again, this r squared is in our denominator, so we could say that 1 over r squared is equal to sine squared theta divided by y squared. Okay, so that's going to be useful to make a substitution for us to go from step 4 to step 5. And then the other substitution we can make is based off tangent theta equals y over x. So that means x is equal to y divided by tangent theta. Another way to say that is x equals y times cotangent theta. Now we don't exactly have an x in our step 4, but we do have a dx. So let's take the derivative. Dx d theta would be negative y cosecant squared theta, or in other words, dx is negative y cosecant squared theta d theta. Okay, so now we have 2 substitutions that we can make back into step number 4. We're going to substitute for r squared, and we're going to substitute for dx. So let's see if we can do this without making things too messy. Step 5, our magnetic field would be mu naught I over 4 pi times the integral of, instead of dx, we're going to say negative y cosecant squared theta d theta. And don't forget, we still have this sine theta to account for. Okay, so times sine theta. And then divided by r squared, or times 1 over r squared. And so that gives us another sine squared theta. So I'm going to make this sine cubed. And then that gives a y squared in the denominator. Now that's a little messy. Let me rewrite and cancel out some quantities. So step 6, and because y is a constant, we can pull that out of the integral. So we get b equals negative mu naught I divided by 4 pi y, right? We've got a y in the numerator and a y squared in the denominator, so I've canceled and I've pulled out the negative sign. And then we're left with the integral of cosecant squared theta sine cubed theta d theta. But cosecant is the same thing as 1 over sine, so cosecant squared is 1 over sine squared. So 1 over sine squared combined with sine cubed just gives me sine. So step 7, we can say the magnetic field at that point is equal to negative mu naught I over 4 pi y times the integral of sine theta d theta. We didn't look at our limits of integration yet. So once again, here's the wire. There's the y-axis and the x-axis. There's the point in question. And so I guess the very first ds we have to account for is way over here. And that's going to be the smallest angle of all. We'll just call that theta naught. Actually, we'll call that one negative theta naught. And then we have to account for this ds and this ds. When we get to this ds, the angle would be 90 degrees. And then the angle starts to get smaller and smaller and smaller again until we get to the final one here. And if the y-axis is on the center of the wire, then this positive theta naught is the same magnitude as this negative theta naught. So we're integrating from negative theta naught to positive theta naught. The alternative to that would be to multiply by 2. So we can say it's negative 2 mu naught I over 4 pi y. And then instead of integrating from this ds to this one, we can integrate from there to there, right? So from 90 degrees to theta naught. Okay. The 2 and the 4 cancel to give us a 1/2. So b is equal to mu, and this is of course the integral of sine theta d theta. So we have mu naught I over 2 pi y, and the integral of sine is cosine. I forgot my negative. And so we get cosine of, the integral of sine is negative sine, isn't it? The integral of sine is negative cosine, excuse me. Okay, so negative cosine theta evaluated from 90 degrees to theta naught. And then I can cancel the negatives, change that one to positive and that one to positive. So I really just have my final result. The magnetic field at that point is equal to mu naught I over 2 pi y times cosine of theta naught minus cosine of 90 degrees, but the cosine of 90 degrees is 0. So final result, here we go. That took a few steps, didn't it? It's mu naught I over 2 pi y times cosine theta naught. So that's the brute force method, right? That's the law of Biot-Savart in order to determine the magnetic field at some particular point of interest. And let's just take it one step further and compare a couple of different wires. So let's compare the magnetic field at point P for wire number 1 that carries a current of I. We can make up a number if we want to call it 5 amps. And we can make up a value for this. We can say we're 2 centimeters away from, actually 2 centimeters, not from the edge of the wire, but 2 centimeters away from the middle of the wire. That's how we define the y-axis. And then wire number 2, we'll say is just, it carries the same current, but it's just much longer. So how would the magnetic fields compare if the point in case number 2 is also 2 centimeters away from the wire? This carries a current of 5 amps. So let's use our result. B equals mu naught I over 2 pi y times cosine theta naught. So let's picture theta naught is the angle from the end of the wire to the point in question. Okay, so plug in the values. Grab a calculator if you've got one. In case number 1, mu naught is 4 pi times 10 to the negative 7th Tesla meters per amp. We have a current of 5 amps, and we've got some cosine theta naught. We'll deal with that in a moment. Divided by 2 pi, and then our value of y is 2 centimeters, or 0.02 meter. So first, let's look at the units. Meters cancel with meters, amps cancel with amps, and so we're going to be left with Tesla. Ooh, and then pi cancels with pi. Oh, this is getting good. 2 times 0.02 will give me 0.04. So I can actually cancel this 4 and call this 0.01. But then again, 0.01 is the same thing as 10 to the negative 2. And 10 to the negative 2 in the denominator can be thought of as 10 to the positive 2 in the numerator. So 10 to the positive 2 combined with 10 to the negative 7th gives me 10 to the negative 5th. So I believe my answer here is 5 times 10 to the negative 5th Teslas, but then multiplied by some cosine of theta naught. And if I compared in case number 2, I think all the values stay the same. I think it's still going to be 4 pi times 10 to the negative 7th times 5 amps divided by 2 pi times 0.02 meter, right? We're still 2 centimeters away, and it's still a current of 5 amps. And all that's going to combine to give me 5 times 10 to the negative 5th Tesla, but there's still a cosine of theta naught that belongs in this equation. Now in this case, if the wire is really long, we can say theta naught is approximately equal to 0, and the cosine of 0 would just give us 1, and so our magnetic field would be 5 times 10 to the negative 5th Tesla. Whereas in case number 1, theta naught might be, I don't know, we can make up a number and call it, just for the heck of it, let's pretend it's 37 degrees. Well, I believe that the sine of 37 degrees is 0.6, and the cosine of 37 degrees is 0.8. So in this case, we would get something more like 4 times 10 to the negative 5th Tesla, right? Because if we multiply 5 times 0.8, that would give us 4. So as long as the wire is really long, we can ignore the cosine of theta naught that shows up. So in general, for a finite length of wire, we say B equals mu naught I over 2 pi y times cosine of theta naught. But if it's we'll either say very long, or I don't know if it's fair to imagine an infinite wire if there's no such thing, but you get the idea. For the very long wire, then, and what do we really mean by that? Very long is just the case where the distance y is very small in comparison to the overall length of the wire. So if the value of y is much, much less than L, then we can say B is approximately equal to mu naught I over 2 pi y, and just leave it at that. Okay.